One of the most important objects of study in linear algebra is the linear transformation, or linear map. These are maps that work kind of like the derivative. Let's let V and W be real vector spaces. A map T from V to W is called a linear transformation. Or a linear map. If it respects linear combinations. And by that I mean that T of C1 V1 plus C2 V2 is the same as C1 T of V1 plus C2 T of V2. Where I'm thinking of V1 and V2 as being vectors in V, and C1 and C2 are scalars. So this says that we can do scalar multiplication addition before applying the map, or we can apply the map first to the vectors and then do scalar multiplication and addition afterward. It doesn't make a difference, we get the same answer. Now I wrote this equation that shows respect for scalar multiplication and addition together, but sometimes it might be easier to check respect of scalar multiplication and vector addition separately. In that case, we can check that T of CV equals CT of V for V in the vector space and C a scalar. And we can check that T of V1 plus V2 equals T of V1 plus T of V2. In case we have a complicated linear transformation, it might be easier to do it this way. But it's fine to do it either way. So for example, let's let V2 and V3 be the spaces of polynomials of degrees less than or equal to 2 and 3 respectively. Now differentiation takes a polynomial of degree at most 3 and lowers the degree by 1. So the result is going to be a polynomial of degree at most 2. So this is linear, and we just have to remember how differentiation works when we add things together, when we multiply by scalars. So if we have a multiple of, let me use P for polynomial, a multiple of one polynomial plus a multiple of another polynomial, that equals, well, scalars come out of differentiation. So derivative of the first polynomial plus C2 times derivative of the second polynomial. That was pretty easy. We could check everything at one time. So doing your scalar multiplication and addition first and then applying the transformation is the same as applying the transformation to the polynomials first and then doing scalar multiplication and then doing addition. Another easy linear transformation involving polynomials is, let's define t from v2 to v3 by sending a polynomial to x times that polynomial. So this map, which is the arrow with a little vertical segment on the left, means maps to. So one thing maps to another is the same as saying t of p of x equals x p of x. So the only difference is here I didn't bother writing the t in the two parentheses. So I don't save a whole lot by doing this, but it's a tiny bit shorter than writing t of p of x equals x p of x. It's just a shorter, the same statement, just it's a little bit shorter to write. So this map t is linear, and to see this we'll take a linear combination c1 p1 of x and c2 p2 of x, and we can take the t to the polynomial separately and see if we get the same thing. So this equals, t is just multiplied by x, so we get x times c1 p1 of x plus c2 p2 of x, which we could rewrite as c1 x p1 of x plus c2 x p2 of x, and then x p1 of x is t of p1 of x, because t means multiplied by x. That's what this is. And then x p2 of x is the same as t p2 of x. Oh, so I guess I've gotten the other version already. So it looks like t of this linear combination is equal to the same linear combination of the t's. So that means t is a linear map. There's another example. I'm going to call this the most important linear map. Let's define t from, I'm going to use a matrix, so let me fix a matrix. Let's say A is an m by n matrix with real entries. And define the map, which I'll call T sub A, from Rm to Rn by taking a vector in Rm and mapping it to A times x. So just left multiplication by A. Well, this is linear basically because matrix multiplication and multiplication of matrices times vectors satisfies all the same rules of distributivity and associativity and commutativity, everything that numbers and variables satisfy. So this is linear because if we look at t sub a of some multiple of x plus some other multiple of y, So I'm thinking of x and y as vectors in Rm. So by the way, this is a 1 by m, sorry, m by 1 matrix. And A is m by n, and x is m by 1. Oh, you know what? I think I've got these indices wrong. Good thing I checked. If we multiply by an m by n matrix, then we're taking a vector in Rn, and we end up with a vector in Rm. So if x is n by 1, and A is an m by n matrix, and we multiply that m by n matrix by an n by 1 vector, then the answer is going to be m by 1. So this is a map from Rn to Rm. So to check linearity, we'll look at two n by 1 vectors, so x and y in Rn. And C1 and C2 scalars, of course. So this is left multiplied by A. So A times C1x plus C2y. That's just A C1x plus A C2y. And the scalars can come out here, which is C1ax plus C2ay, which is C1 times TA of x plus C2 times TA of y. So this is linear basically because of this first expression being equal to this last expression. We can do the scalar multiplication and addition first and apply the linear transformation, or we can apply the linear transformation to the vectors first and then do scalar multiplication and add last. We get the same answer. Now I'll say more in another video about why I'm calling that the most important linear map. So related map is, let's fix A again, but I'm going to make it an n by n matrix. And I'm going to define a map from n by n matrices to n by n matrices. By taking a matrix B and left multiplying it by A. Very similar to the previous map where we're multiplying a vector on the left by A, but now we're multiplying a matrix on the left by A. Now this is linear for the same reason. That is, if we take T of C1, let's say B1 and B2 are two different matrices, that equals A times C1B1 plus C2B2. And then we can just distribute the A and we get A C1B1 plus A C2B2, which is C1A B1 plus C2A B2, just taking the scalars out, which we can do with matrix multiplication. And this is C1T of B1 plus C2T of B2. So that's linear also. I guess it wouldn't hurt to have an example of a map that's not linear. So let's do an example of a nonlinear map. So let's keep the n by n matrices. And again, we'll fix an n by n matrix A. Let's define a map T from n by n matrices to n by n matrices by taking a matrix B and adding A to it instead of multiplying. Now let's compare T of C1 B1 plus C2 B2 and C1 T of B1 plus C2 T of B2. These should be equal if T is linear. So we have T of C1 B1 plus C2 B2 equals, T just means add A. So I guess it's going to be C1 B1 plus C2 B2 plus A. So we have that, and if we take C1 T of B1 plus C2 T of B2, then T of B1 is B plus A. T of B2 is, B1 plus A. T of B2 is B2 plus A. And if we multiply out, we get C1 B1 plus C2 B2, which looks just like that. And then we get C1A plus C2A. So the problem is that this is not equal to A, well, unless C1 plus C2 equals 1. But when we check linearity, we're doing this for arbitrary constants. We're not allowed to say, well, the constants have to equal 1 when you add them together. So this is not true for all constants C1 and C2. So this means that the map is not linear. All right, let me do a harder example now. Let's let V be polynomials of degree less than or equal to 2. We'll define a map from V to itself by sending a0 plus a1x plus a2x squared, so that's our typical polynomial of degree at most 2, to a0 minus a2 plus a0 plus 3a1x plus 2a0 x squared. So let's check to see if that's linear. And I think this is complicated enough that I would check respect of scalar multiplication and respect of addition separately. Alright, so let's check them and see what happens. Alright, so if we have a real number c, t of c times this polynomial, a naught plus a1x plus a2x squared equals t of c a naught plus c a1x plus c a2x squared, which is, now the linear transformation says take the 0th coefficient and the second coefficient, subtract them, and that becomes the constant term. So c a naught minus c a2 is the constant term. And then the coefficient of x is going to be constant term plus 3 times the coefficient of x. So plus c a naught plus 3c a1x, because I took the constant term and 3 times the coefficient of x. And then the coefficient of x squared is going to be 2 times the constant term. Just forget about the a2. So plus 2c a naught x squared. Alright, so I'm wondering if this is c times the transformation applied to just the polynomial. Well, I can factor c out from everywhere. So this is c times a naught minus a2 plus c times a naught plus 3a1x plus c times 2a naught x squared. And now I can factor c out really from everywhere and put it in the front. And when I do that, I've got a naught minus a2, a naught plus 3a1, and 2a naught as my coefficients. So after I factor out c, what I've really got is t of a naught plus a1x plus a2x squared. So at least this respects scalar multiplication. Now let's check addition. And maybe I don't want to erase the definition here, so I'll erase the top part and I will start again. So this t respects scalar multiplication. Alright, so what happens if we have two different polynomials? So now let's consider t of a naught plus a1x plus a2x squared plus, say, b naught plus b1x plus b2x squared. Hopefully this is going to be equal to t of the first polynomial plus t of the second one, but we'll see. Alright, so we need the constant term and the coefficient of x and the coefficient of x squared. So let's combine these. So we've got a naught plus b naught as the constant term. And the coefficient of x is a1 plus b1. And the coefficient of x squared is a2 plus b2. Alright, t of a polynomial like this is subtract the constant term and the coefficient of x squared. So we've got a naught plus b naught minus a2 minus b2 is the constant term. And then for the coefficient of x, it's going to be constant term plus 3 times the coefficient of x, plus a naught plus b naught plus 3a1 plus 3b1 x, and then the coefficient of x squared is going to be 2 times the constant term. So plus 2a naught plus 2b naught x squared. Alright, so if I separate out, and I'm hoping this is going to be t of the first polynomial plus t of the second polynomial. So maybe if I separate out the a's and the b's, I'll be able to see that. So this is a naught minus a2. I'm going to put the a's on the left and the b's on the right, plus b naught minus b2. And then for the x, we've got a naught plus 3a1 x, and then with b's, we've got b naught plus 3b1 x. And if we look at the x squared and the a's, we've got plus 2a naught x squared, and then plus 2b naught x squared. So the a parts add up to exactly this. This is t of a naught plus a1x plus a2x squared, and then the b parts actually add up to that also. So that's plus t of b naught plus b1x plus b2x squared. So t respects addition too. And since we checked to see that it respected scalar multiplication before, it is linear. So there we have it. There's our difficult example. The end.